Hello, class. Today we're going to put a bunch of pieces together, and we're going to talk about the chromatic numbers of planar and toric graphs. And so, you want to know what's special about planar and toric graphs, that we're able to say something more about the chromatic number. You have to remember that we have laying around in our back pocket this Eulers Theorem that says that if you're looking at a planar slash toric graph, then you have this relationship that this thing is this Euler characteristic, which is 2 for planar graphs and 0 for toric graphs. Okay. I also want to remind you that last time we had this whole idea that if delta of g, big delta of g, was the max degree, then we could show that the chromatic number of a graph was less than or equal to that big delta of g plus 1. Okay, and this was basically a pigeonhole principle argument. It was basically an argument that if you do this in the silliest possible way with no thought whatsoever, you'll succeed. Okay, so this time we're actually going to look at something which seems backwards. Namely, we're going to look at a variation on this big delta. Namely, we're going to look at little delta of g, which is going to be the min degree of a vertex in g. And what I want to do is I want to figure out, okay, what is this number for planar graphs and toric graphs? Okay. And so I'm going to go ahead and make a claim here. If you want, this is going to be a lemma in our theorem, which is that if g is planar, then delta of g is no bigger than 5. And if g is toric, that is, if you can embed it on the surface of a torus, delta of g is no larger than 6. Okay, now I'm going to prove this claim, but I want to convince you this claim is interesting in its own right. Because this is not at all obvious that if I try and draw some graph in the plane and draw as many connections all over the place as I possibly can, I can definitely, for example, in the plane, have a graph with vertices of very high degree. So I could take what's often called the wagon wheel graph, where I take the cyclic graph on n vertices, which is definitely planar, stick a dot in the middle for an extra vertex, and then connect all of these to the center. And this graph definitely has a vertex of very high degree. So whatever, in fact, degree you want, you can make this that degree. So what we've just said here, sort of an observation, is that big delta of g is actually unbounded for planar graphs. So planar graphs can have a single vertex of as high degree as you want. They can have 3 vertices of degree as high as you want. You can string these together. But there's this sort of secret constraint that no matter how you arrange the edges on one of these planar graphs, always you're going to end up with a vertex whose degree is small, at least in that it's not larger than or equal to 5. Sorry, it's not larger than 5. It could be equal to 5. Okay, so how is this proof going to go? Well, I'm going to try and relate this little delta to all of my pieces of Eulers' theorem. That is the number of vertices, the number of edges, and the number of faces. Okay. So, namely, I want to recall this handshaking lemma that if I take the sum across all the vertices of a graph of the degree of that vertex, I get exactly twice the number of edges. But now, this number is certainly larger than or equal to just summing delta of g vertex many times, right? Every one of these degrees is individually at least as big as delta, because delta is the smallest degree. And so if I add them all together, I get something that's at least as big as delta of g, which means that the number of edges here is, which means that the number of vertices is less than or equal to twice the number of edges divided by this delta of g. Again, probably this bound is terrible, in the sense that if there's some huge degree vertex, I'm totally not counting it. But this is at least true. Namely, you're always going to get this identity. Okay, so we have this relationship on the number of vertices. I also want to think about the number of faces and how that relates to the number of edges. And remember, the relationship between faces and edges comes back to this notion of walls. And so the idea was that this face here has 4 walls, and then this outer face also has 4 walls. So the number of walls, on the one hand, literally is equal to twice the number of edges, because every edge corresponds to 2 walls, pretty transparently. But also, every face has at least, every face has at least 3 walls, and so the number of walls is greater than or equal to 3 times the number of faces. And so what does that say? That says that 2e is greater than or equal to 3f. So the number of faces is less than or equal to 2 times the number of edges over 3. Okay, so there's 2 pieces of this story, and so basically I've here related everything back to the number of edges and to this mysterious number delta, which is the smallest degree of any vertex. So now I want to think about what all of this tells me about Eulers' theorem. And remember that Eulers' theorem concerns this quantity, number of vertices minus the number of edges, plus the number of faces, and that this is equal to some asterisk, where, remember, I'm here simultaneously talking about both planar and toric graphs. So this asterisk is either 0 or 2, depending on which I mean. So this asterisk is 2 if planar, and it is 0 if the graph I'm talking about is toric. Okay, but I'm just going to leave the asterisk alone for the moment, and I'm just going to look at how the asterisk is defined in terms of this vertices minus edges plus faces. So, namely, asterisk equals the number of vertices minus the number of edges plus the number of faces. Okay, and I have 2 inequalities here. One that overestimates, one that overestimates the number of vertices and one that overestimates the number of faces. So I'm going to plug both of those in, which is going to give me an overestimate of asterisk. Okay, so this is less than or equal to twice the number of edges over delta of g minus the number of edges plus twice the number of edges over 3. Okay, so all I did here was use this to overestimate the number of vertices and this to overestimate the number of faces. Okay, so now I notice, hey, this thing I can factor out the number of edges. And so this is the number of edges times, okay, and so this is 2 over delta of g. Let's see, and so this is minus 1 plus 2/3, so that's minus 1/3. So this is the number of edges times, okay, and so I'm going to put this over a common denominator, so times 6 minus delta of g over 3 times delta of g. Okay, so here is something, and again, remember the thing we've shown is that this asterisk, whatever it happens to be, it's less than or equal to this number. 6 minus delta of g over 3 times delta of g times number of edges. Okay, now, how can I get any information out of this? Well, this thing here is positive. This thing here is positive. And this thing over here, depending on whether we're in the case of the torus or the planar, it's either positive, in which case it's 2, or it's 0. Okay? And so if asterisk is 2, then this thing is positive, and so then this side must be positive, because it's bigger than a positive number. And this is the only thing we don't know is positive. And so then 6 minus delta g has to be positive. Sorry, that's a delta of g. It looks kind of like a delta of 6, especially since it's right next to a 6. But 6 minus delta of g is positive, so delta of g is strictly less than 6. So delta of g is less than or equal to 5. And that proves that case that we wanted before. Okay. On the other hand, if asterisk is 0, then all I know is the left-hand side is non-negative. So I know this must be non-negative because all these things are positive, so this must be non-negative. So then 6 minus delta of, let's see if I can make a g this time, must be greater than or equal to 0. So delta of g is less than or equal to 6. Okay, that time I really concentrated and got it to look like a g. This time it looks like a 6 again. Okay, but those two pieces, those both prove my claim. Okay, so every planar graph has a vertex of degree 5 or less, and every toric graph has a vertex of degree 6 or less. Okay, so we're going to use that when I talk about how many colors it's going to take to color one of these graphs. Okay, so now I'm going to shift my focus to a planar graph and talk just about planar graphs for a bit. Okay. So a planar graph we want to talk about its chromatic number. Okay. And so really what I'm interested in is what is the largest chromatic number among all planar graphs. Okay, and I'll point out there's no reason a priori to expect that there's any finite answer to this question. There's no reason to suspect, okay, well, there's definitely no planar graph whose chromatic number is 20, or definitely no planar graph whose chromatic number is 1,000,000. A priori, there's no reason to suspect that this is finite. Okay, so I want to imagine here that we have a table, and I'm going to think about for each n, how many vertices must a planar graph have to have chromatic number n? Okay, so we have a table here, where on the one hand, I'm going to have n, and on the other hand, I'm going to have a number of vertices. Okay, so this chart is going to start off pretty boring. So 1, well, the number of vertices, it has to be, well, as soon as you have one vertex, your chromatic number is 1. Okay, how many vertices does it take to get a graph of chromatic number 2 in the plane? Well, there you go. There's a graph with 2 vertices. Its chromatic number is definitely 2. Okay, what about 3? Well, here's a graph with 3 vertices. Its chromatic number is definitely 3. What about 4? Okay, well, there's a graph with 4 vertices. Its chromatic number is 4. Okay, so your pattern recognition at this point, you're a math major, your pattern recognition is pretty good, so we think, okay, well, this 5 is going to be 5. Okay, but if you look at what we actually did, we actually wrote down K1, K2, K3, and K4. Those were exactly the graphs we drew. So here you'd want to draw K5. Except remember, K5 is not planar. That's something we proved before. Every graph on 5 vertices is a subgraph of K5. And as soon, we proved this too, as soon as you remove an edge from K5, it's now 4 colorable and planar. So what that says is this number here, it's got to be at least as big as 6. But who knows what it actually is? You could go through all the graphs with 6 vertices, and you could figure out, okay, of those that are planar, which ones have chromatic number 5 or 6 or whatever, and so on and so forth. So I'm going to jump here. I'm going to jump up a bit, and I'm going to jump to n equals 6. Okay, so I am going to suppose that, actually, I'm going to jump straight up. I'm going to jump all the way up to 7. So I'm going to suppose that there is a graph, a planar graph, with chi of g equals 7. Okay. And so there's some chart here, some number. I'm just going to write n5, or sorry, v5, whatever. And then this chart continues. Okay, n size of v6, 7. And then so here's v6, here's v7. Okay. So all I'm assuming here, when I suppose this, is that this v7 is finite. Namely, there is a graph with v7 vertices that has chromatic number 7. So I'm going to suppose there's a planar graph with chromatic number 7, and that the size of G is V7. Which is to say that G has the smallest number of vertices a planar graph with chromatic number 7 could have. Okay, so I have my smallest planar graph whose chromatic number is 7. Okay, and we know it has at least 7 vertices, and you could probably convince yourself it has to have at least 10 vertices by just checking all the graphs smaller than that, and maybe if you check some more, you could convince yourself it has to have at least 12 vertices, and you could do some computer search, and you could get up to that this graph has to be pretty big. Okay, but I want to phrase this in a more striking way, which is to say, if we delete a vertex from G, it can be colored in 6 colors. Okay. Why? Well, because we assumed that G is the smallest possible graph that is planar and requires 7 colors. So if I delete a vertex, that graph is now smaller, which means that it's smaller than G, which means that it can no longer be colored in, or no longer takes 7 colors to color, so it takes 6, or maybe it takes 5. Uh, can't take 5. You can convince yourself we'll have chromatic number exactly 6, but its chromatic number is also at most 6. Okay. So here's where we put this whole circle of ideas of taking the smallest graph, whose chromatic number is 7, together with the thing we proved before, which is that if you take a planar graph, there's always a vertex of degree 5 or less. Okay, so I'm going to let and let's give it some fancy name. Let's let X in the vertex set of G be a vertex of degree less than or equal to 5. This definitely exists by what we proved earlier. Okay, and so I'm going to draw a picture of the graph G. And so this is just a random thing. So there's a lot of stuff I don't know that's going on, where things are connecting all over the place. Who knows what's happening? But somewhere in the center of all of this is this vertex X. And this vertex X is connected to, at most, 5 other vertices. Okay, so here I've drawn a case where this vertex X is connected to exactly 5 other vertices, but it could be connected to 4 or 3, who knows? Some number that's at most 5. So I'm going to remove all of this from G. Okay, so I'm going to make the graph G hat, where I take G and I remove the vertex X and remove all the related edges. That is, all the edges connected to x. Okay. So in other words, g hat is just the black graph here, where I guess I should have left these vertices as black, but I've taken the red part away. By assumption, we can color g hat in 6 colors. Right? Because remember, G itself was the smallest graph that required 7 colors. And so if I take a vertex away, I now have a smaller graph. That graph can't require 7 colors anymore, so it can be done in 6. Okay, so I've got now my coloring on this. So I'm going to do that. So I color this thing in 6 colors, and let's just say here this vertex ends up blue, this one over here ends up blue, this one over here ends up green, this one over here ends up orange, and this one over here ends up yellow. But I color all the vertices in this whole graph, everything in G hat, in 6 colors. Color G hat in 6 colors. And now I'm going to put x and its edges back in. Okay, so we'll put x back in. I'll put its edges back in. But here's my claim. I can also color x in one of those colors. Why? Well, x is only connected to at most 5 vertices. And those 5 vertices each have a color. That knocks out at most 5 colors. So because of the pigeonhole principle, in fact, this is exactly the same instance of the pigeonhole principle that showed up way earlier when we were talking about this theorem, when we were proving that the chromatic number is always less than or equal to the biggest degree plus 1. Here I now have the degree of x, it's 5 or less, and so at most 5 colors are knocked out, but I've got 6 colors, great. Only 5 colors out of 6 have been eliminated. And I should say here, at most 5 colors out of 6 have been eliminated. Okay, great. So I colored my graph in 7 colors. I plucked out this one point, colored what was left in 6 colors, put this point back in, colored it in one of those 6 colors. Wait, what have I done? Well, what I've done is actually to color G in 6 colors. And so, thus, what have we actually shown? We've actually shown that chi of G is, in fact, at most 6. But that's a contradiction, because how did I start with this whole thing? I started by supposing that there was a graph that was planar with chromatic number 7, and then I chose the smallest one from there, and blah, 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 blah. Okay. So this is a contradiction, and the thing I contradicted was there being a graph that was planar with chromatic number 7. Okay, and thus we've proven what is known as the 6-color theorem. So here is the 6-color theorem. Every planar graph can be colored in 6 colors. Or if you want, you could phrase this as if G is planar, then chi of G is at most equal to 6. Okay, so we have proven this. It's ours. Now, what we haven't proven is that there is a graph that requires 6 colors. In fact, there's not a graph that requires 6 colors. And so, if you want, you could do some more work, and you can actually get to that if G is planar, then chi of G is less than or equal to 5. Okay. And so this is uncreatively called the 5-color theorem. I'm not going to prove this for you, but if you want, this is definitely within your reach. So if you just Google or look on YouTube for 5-color theorem, you can definitely find plenty of proofs of this. Now, what turns out to be surprising is, in fact, this isn't the best either. There is no planar graph that requires 5 colors. Okay, and you might have sort of seen small shadows of this in the fact that K5 is not planar. And so K5 would be the obvious graph to require 5 colors, but you could imagine some really complicated graph that didn't have a K5 in it, but somehow still required 5 colors. Okay. But that's a little bit tricky to prove doesn't exist. But in fact, here is the best possible theorem. This is what's called the 4-color theorem. Which is that if G is planar, then chi of G is less than or equal to 4. Okay. And in fact, this proof is really hard. Okay. And in fact, this proof is so difficult that we know no proof of this that does not require a computer. Okay, now I want to emphasize, because it's sort of easy to imagine, maybe you no longer suffer from this because you've grown up with computers and so you trust the things computers tell you. But it's easy to sort of interpret this to say that when I say the proof requires a computer, that what I'm talking about is that a computer checked a whole bunch of examples and didn't find any counterexamples, so we decided that this is true. That's not actually what happened. The computer really does make a proof, and here's a basic outline of how that happens. What happens is that when you go to prove this, you realize that it's going to be a case argument. And it's going to be a really ugly case argument. In fact, it's going to be a case argument with tens, if not hundreds of thousands of cases. And no human wants to do a case argument with tens, if not hundreds of thousands of cases. But fortunately, each of the cases is completely algorithmic to check. And so once you have reduced this to this finite but ridiculous number of cases, then you can just have the computer iterate over all of them and check them all, and then you're done. Okay. So way back in the olden days, when I was an undergrad or whatever, there was a lot of philosophical debate about, okay, this proof required a computer. Is that really a proof? Is it a proof if a human doesn't do it, if a human doesn't write down all of these things and really check them? And I think everyone on the side of the argument that it doesn't count if a computer does it has expired. We're now sort of in an age where computers are intimately connected with the art of doing math. And mathematicians did a lot of very hard work to get this to the point where there were only 700,000 cases, or however many there were to check, so that a computer could check it. so that we now know that this is really a theorem. Okay, and that is now indisputably a valid proof method. So this is sort of this story. Okay. I want to make an aside about this, and then I want to talk about what happens if you look at graphs on a torus. But first, an aside. Okay, here's my aside. The way this four-color theorem is usually stated is it's usually stated in terms of maps. So it's usually stated as, hey, let's suppose you break the world into regions, and you have these sorts of things like this, and someone is trying to make a map of this region, or this region with all of these countries or whatever, and the cartographer is making the map, and they want to color each country of the map in its own color, such that no two touching countries are the same color. In fact, if you look at a map, that's what they typically do. They exactly color each country in a color so that it doesn't have the same color as an adjacent country. Also, additionally, if you want to throw in this constraint, they color all of the water blue, and they don't color any of the countries blue. But you do this, and then the claim, as it's usually stated, particularly if someone's talking about this to high school students or whatever, and if there are high school students in your life and you want to talk to them about this, this is a great way to frame this problem. You can always do this in four colors, again, assuming you ignore the bit about the water being blue. Okay. And this maybe at first seems like this is a completely different question than the question we were just talking about, namely the question we were talking about with planar graphs, because where are the vertices? Here, if anything, it looks like what I'm coloring are faces. But I can reframe this question completely into a question about coloring the vertices. And here's how I do that. What I'm going to do is I'm going to make a vertex on each face. Like this. Okay. And so coloring the countries is now equivalent to coloring the vertices. But what I'm going to do is I'm going to draw an edge that connects each pair of adjacent countries. So for example, these two are connected, 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 and so on. Okay, and once we've done this, we get a planar graph. So the blue, if I pull out all the dots and edges, that's a planar graph. And if you believe the four-color theorem, then you can color that planar graph in four colors. And then you could just use the color of each vertex to color that region. Now, if you're attentive and curious, you might say, well, how on earth do I know that the rule you just described will actually give me a planar graph? And the reason is because you can arrange it so that the edges here always pass over the border between the two countries. And since there's only one border between each pair of countries, or rather I should say, since each border only has two countries, one on either side, then I'm never going to intersect those two things. And so by doing this, I'm exactly using the fact that these two regions border each other in order to draw this line in such a way that it doesn't intersect with any of the other edges. Okay, and so on all the way through this. And so as long as you are mindful to make sure that your edges, and here's another one I missed, actually go over the border of the country that they're on, then they won't intersect, and you'll end up with this planar graph beautifully, so that you can apply the four-color theorem. And so this is just a completely equivalent way of framing exactly the same question. Okay, so that is aside number one. I guess this next one isn't exactly an aside, but this is a further question. So, further question. So we talked a lot about toric graphs. So you could ask the same question. Okay, every graph that you can put in the plane can be colored in 4 colors. What about graphs that can be put into a torus? What can I say about the chromatic number of those? Okay, so you might remember that, oh hey, the graph K5 can actually be put in a torus. So what that's saying, the only reason I bring up this specific example, is that this shows me the 4-color theorem is definitely not true for graphs on a torus. There are graphs, such as K5, on a torus that require 5 colors. Right, and so you could wonder, okay, what about requiring 6 colors, 7 colors, 8 colors, so on and so forth? You could figure this out. But I want you to recall from earlier that we proved that if G is toric, then G definitely has a vertex of degree less than or equal to 6. So I want to recall that. And then I want to think through our proof of the 6-color theorem. Namely, our proof of the 6-color theorem started by saying, okay, suppose that I have a planar graph which requires 7 colors. And then goes on through this, and then you say, okay, now suppose I have a minimal graph that requires 7 colors, and then I'm going to find that vertex of low degree. I'm going to pluck it out. Now my graph can be colored in 6 colors, and now, oh, oops, now I can go back and put that vertex back in, and now I can color it, and I don't need to use the 7th color at all. Well, what would we get if we did the same thing, but for toric graphs? So the first thing is to note, I need to change the place I start. So with planar graphs, I started at 7, because 6 is 1 more than 5, and I knew there was going to be a vertex at degree 5. For toric graphs, I have to start at 8, because I know there's going to be a vertex of degree 6 or less. Okay, so suppose there's a toric graph with chromatic number 8. And then that means there's automatically a smallest graph, a smallest toric graph with chromatic number 8. Okay. Well, by this theorem about the little deltas, there's some vertex of degree at most 6. Let's call that vertex x. Okay, so we have a picture like this, except maybe now this thing actually has degree 6. So there's some other thing here down here that's colored in some other color. I guess I'll color it in black, boringly enough. And so I've now got this vertex here that is adjacent to 6 things at most, and I use the 6 colors there. Okay, but I can only have used 6 colors, so there's a 7th color in particular that I've used to color the whole graph. And so I can actually use that color to color this vertex, which means my graph is actually now 7 colorable, which means that our graph that I assumed required 8 colors to color on the torus actually could be colored in only 7. And so what have we proven? We have proven the following theorem, and we really have completely proven this. If you go write out all the details, we've completely proven this. If G is a toric graph, then G can always be colored in 7 colors. Okay, so that's ours, in just the way that we proved that every planar graph could be colored in 6 colors. So the natural question is, okay, well, that's what you were able to do. That's what we were able to do. So what's the real answer? If 7 is what we can prove easily, or relatively easily, what's the actual answer? Well, we know K5 is toric, so we know the number can't be worse than 5. So it would be really natural for you to guess, based on everything you've seen in this lecture, that maybe there's a 5-color theorem for the torus. Maybe every toric graph can be colored in 5 colors. But if you think back to what we've talked about before I showed you this picture. And this picture, if you'll recall, is a demonstration of embedding the graph K7 into the torus. There it is. Okay. And K7, the complete graph on 7 vertices, definitely can't be colored in fewer than 7 colors. And so we've proven the 7-color theorem for graphs on the torus, but also the 7-color theorem for graphs on the torus is the best possible theorem. And so since K7 is toric, this is the best possible. And so this is really interesting, actually. Somehow, in the plane, which you think of as being way simpler than a torus, we end up with this problem that's so hard you can't do it without a computer to check through your thousands and thousands of cases. But on the torus, which we think of as being much more complicated than the plane, the same proof gets us to the best possible theorem. Okay, we'll wrap up there for talking about colorings of graphs and colorings of planar graphs and toric graphs and all of these sorts of adventures. But we'll pick up next time and we'll talk about Eulerian paths in graphs and what that means. And we'll talk a little bit about Hamiltonian paths in graphs and what that means. But until next time, be well.